This is an audio recording for visually impaired student. Unit Thermodynamics, Physical Chemistry, Maxwell equation. Delta H is equal to TdS plus VdP. Delta G equal to minus VdP minus SGT. Curly S by curly V with respect to constant temperature equal to curly P by curly T at constant volume. First law of thermodynamics. Based on conservation of energy, energy remain constant. Second law of thermodynamics, entropy of universe is continuously increasing. Thermodynamics, it implies flow of heat. It deals with energy changes accompanying all type of physical and chemical process. Basic terms of thermodynamic system. A system may be defined as that part of universe chosen for thermodynamic consideration to study the effect of temperature, pressure, etc. called system. Surrounding. The rest of universe which might be in a position to exchange energy and matter with the system is called surrounding. Types of system. First, open system. A system which can exchange matter as well as energy with its surrounding called open system. Closed system. A system which can exchange only energy with the surrounding but not matter called closed system. Third, isolated system. A system which can neither exchange energy nor matter with the surrounding is called isolated system. Homogeneous and heterogeneous system. First, homogeneous system. A system is said to be homogeneous if it is uniform throughout. Homogeneous system consists of only one phase. Example, pure solid, pure liquid, etc. Second, heterogeneous system. When a system is not uniform throughout, a heterogeneous system consists of two or more phases. Thus, a system consisting of two or more immiscible liquids or a solid in contact with a liquid in which it does not dissolve, a mixture of two or more solids. Macroscopic system. The system in which there are large number of particles like atoms, ions, molecule, etc. Macroscopic property. A property associated with the collective behavior of particle in a macroscopic system called macroscopic property. Example, pressure, volume, temperature, etc. State of a system. When macroscopic properties of a system have definite value, the system is said to be in definite state. If any one of the macroscopic property of the system changes, the system is said to be in a different state. The first and last state of a system is called initial and final state. State variables. Since the state of a system change with change in any of the macroscopic properties, these properties are called state variable. Composition, pressure, temperature, volume are most important state variables. Equation of state for an ideal gas. PV equal to RT. Independent variables pressure and temperature. Dependent variable volume. Thermodynamic equilibrium. A system is said to be in thermodynamic equilibrium if the macroscopic properties of the system in various phases do not undergo any change with time. A heterogeneous system consists of more than one phase. The thermodynamic equilibrium implies three different types of equilibria which must exist simultaneously. These are first, thermal equilibrium. If there is no flow of heat from one portion of the system to another, this can happen if temperature of the system remains constant. Mechanical equilibrium. If no work is done by one part of system over other, this is possible if the pressure remains constant. Third, chemical equilibrium. If no change in composition takes place in any part of the system with the passage of time. Extensive and intensive property. First, extensive properties. Those properties which depend upon quantity of matter contained in the system. Example, mass, volume, energy. Second, intensive property. These properties are independent of amount of substance present in the system. Example, temperature, pressure, density, viscosity. Thermodynamic process. The operation by which a system changes from one state to another state. This change is accompanied by change in energy. Different types of process. 1. Isothermal process. Temperature remains constant throughout the process called isothermal process. Second, adiabatic process. When a process is carried out in such a manner that no heat can flow from the system to the surrounding or vice versa, that is system is completely isolated from the surrounding called adiabatic process. Third, isochoric process. The process during which the volume of the system is kept constant. Fourth, isobaric process. It is the process during which the pressure of the system is kept constant. Reversible and irreversible process. First, reversible process. A process which is carried out infinitesimally slowly so that the driving force is only infinitesimally greater than the opposing force. Work produced in a reversible process is maximum. Second, irreversible process. A process which does not take place infinitesimally slowly called irreversible process. For such process, driving forces are much greater than opposing forces, so these can't be reversed. These are also called spontaneous process. All natural processes are irreversible. Example, flow of heat from high temperature to low temperature. Internal energy delta U. It is the total energy associated with the system by virtue of its molecular constitution and motion of its molecule. It depends upon internal potential energy and internal kinetic energy. Delta U, if U1 greater than U2, then delta U will be negative. If U1 less than U2, then delta U will be positive. Delta U negative, energy is evolved. Delta U positive, energy is absorbed. Units of U, ERGS or joule. 1 joule equal to 10 to the power 7 ERGS. For cyclic process, delta U equal to 0. Work. Work is equal to external force into displacement. Work done is equal to a generalized force called intensity factor into a generalized displacement called capacity factor. F external is equal to P external into area. Work is equal to minus P external into area into delta L. Work done by the system equal to negative expansion. Work done on the system positive contraction. Heat Q. When heat is given by the system to the surrounding, it is given a negative sign. When heat is absorbed by the system from the surrounding, it is given a positive sign. Units calories SI unit joule. 1 calorie equal to 4.184 joule. State and path function. A thermodynamic quantity is called state function. The change of state function depend upon initial and final state. Example, pressure, temperature, volume and energy are state function. Work is not a state function. Path function. A thermodynamic quantity whose change in the value depend upon the path followed during a process is not a state function, but it is sometimes called path function. Heat and work are not state function but are path functions. Thermodynamic quantity can be obtained by integration and differentiation only if it is a state function. Laws of thermodynamics. Zeroth law. When two bodies are in thermal equilibrium with a third system, then in turn they are in thermal equilibrium with each other. T1, T2, T3 equal T1 equal to T2 equal to T3, also known as law of thermal equilibrium. If a body A is in equilibrium with body B and body B is also in equilibrium with body C, then bodies A and C are in equilibrium with each other, or system A and C are placed in contact with each other, no exchange of heat will take place. Second, first law of thermodynamics. Based on conservation of energy, according to first law of thermodynamics, energy can neither be created nor be destroyed, although it may be converted from one form to another. Or total energy of the universe remains constant, although it may undergo transformation. Or energy of an isolated system is constant. For example, the electric energy supplied to a heater is converted into heat, whereas electric energy passing through the filament of a bulb is converted into light. This law is purely result of experience. There is no theoretical proof for it. The following observation justify the validity of this law. Whenever a certain quantity of some force of energy disappear, an exactly equivalent amount of source or either form of an energy must be produced. Second, it is impossible to construct a machine which produces work continuously without consuming energy. Third, a particular amount of work done always produces same amount of heat respective of how work is done. It means for every 4.184 joule of work done, 1 calorie heat is produced or vice versa. Mathematical expression of first law. We know that internal energy of a system changes under two conditions. First, when exchange of heat takes place between system and surrounding, it means when heat is absorbed by the system or given out by the system. Second, when work is done on the system or by the system. Consider a system whose initial internal energy is equal to U1. If a system absorbs heat Q from surrounding, then internal energy is equal to U1 plus Q. If work is done on the system, then internal energy further increases and become U2, that is U1 plus Q plus W. Total energy is equal to U1 plus Q, equation 1. U2 is equal to U1 plus Q plus W, equation 2. U2 minus U1 equal to Q plus W. Delta U is equal to Q plus W. So delta U is equal to Q plus minus W. If delta U is equal to Q plus W, work is done on the system. If delta U is equal to Q minus W, work is done by the system. Limitations of first law of thermodynamics or application of second law of thermodynamics. First, first law does not put restriction on the direction of flow of heat. First law established the relationship between heat absorbed and work done by the system. It places no restriction on the source of heat or on the direction of its flow. According to first law of thermodynamics, heat is always found to flow from hotter to colder body. Thus, first law is unable to tell the direction of flow of heat. Second, first law has no criteria for spontaneity of a process. There are several natural processes which take place of their own in one direction only, but don't proceed in reverse direction on their own. Example, flow of heat from hotter to colder expansion in vacuum, burning of fuels, these are spontaneous processes. According to first law, use in the heat content is the reason for spontaneous. This means function in which heat is lost is spontaneous, whereas a reaction in which heat is absorbed must be non-spontaneous. Limitations of first law need for the second law. First, according to first law, energy of an isolated system remains constant during a specified change of state. Second, the first law states that energy of one form can be converted into an equivalent amount of energy of another form. But it does not tell that heat energy cannot be completely converted into an equivalent amount of work. The second law helps us to determine the direction in which energy can be transformed. It also helps us to predict whether a given process or a chemical reaction can occur spontaneously. It introduced a new concept of entropy. Third, but there are some processes in which heat is absorbed, still the reaction proceeds spontaneously, such as vaporization of wet water at low temperature. Fourth, as stated by first law, the exact equivalence between heat and work is not possible. Second law of thermodynamics, Calvin's statement. It is impossible to use a cyclic process to transfer a heat from a reservoir and convert it into work without at the same time transferring it from hotter to colder. Or it is impossible to convert heat completely into work without leaving some effect in the system and surrounding. Calvin Planck's statement. It is impossible to construct a machine which operates solely by removal of heat from a single thermal reservoir and it to equal amount. Clay's statement. It is impossible to construct a machine that is not able to transfer heat by cyclic process from colder to hotter body without the work of external agency. Efficiency. Eta is equal to Q2 minus Q1 by Q2 equal to T2 minus T1 by T2, where Q1 equal to heat of sink, Q2 equal to heat of source, T1 equal to temperature of sink, T2 equal to temperature of source. 1 minus Q1 by Q2 equal to 1 minus T1 by T2, so Q1 by Q2 equal to T1 by T2. Q1 by minus T1 equal to Q2 by T2, that is Q reversible by T equal to constant, minus Q1 by T1 equal to Q2 by T2, that is Q1 by T1 not equal to Q2 by T2 equal to 0. If summation Q by T equal to 0, reversible. If summation Q by T is greater than 0, irreversible. Delta S total is equal to delta S reversible plus delta S irreversible. So delta S total is greater than equal to 0. Third law of thermodynamics. The entropy of all perfectly crystalline solid may be taken as zero at absolute zero temperature. At absolute zero, the system must be with maximum possible energy. Entropy is related to the number of accessible microstate, and there is typically one unique state called ground state with minimum energy. In such cases, the entropy at absolute zero will be exactly zero if the system does not have a well defined order or glassy order. Then there will remain some finite entropy as the system is brought at very low temperature, either because the system locked into a configurational with non minimal energy. The constant value is called the residual entropy of a system. The entropy is essentially state function. S is equal to R into ln of W equal to K n into ln of W, where W is equal to thermodynamic probability and R equal to gas constant. Limitations of third law. The third law is not applicable to supercooled liquid, gaseous, solid. Even at 0 Kelvin entropy, they have residual entropy. Residual entropy. It is the difference in entropy between a non-equilibrium or a crystal state of a substance close to absolute zero. It describes the entropy at 0 Kelvin of a glass and plastic crystal referred to the crystal state whose entropy is 0. According to third law of thermodynamics, it occurs if a material can exist in many different states when cooled. The most common example is glass. A common example is a case of carbon monoxide, which has a very small dipole moment as the CO crystal is cooled to absolute zero. Few of the CO molecules have enough time to align themselves in a perfect crystals with all CO molecules oriented in the same direction. Because of these, the crystal is locked into a state with two and different corresponding microstate given a residue entropy, that is S is equal to R into ln of W. S is equal to R into ln of 2 to the power n, co-arranged in manner like head to tail. The head to tail alignment has lower energy due to interaction of opposite charge dipole, where head to tail have higher energy. Opposite charge solid having mixture of isotope don't have zero entropy at 0 Kelvin. So delta S mixture is equal to minus R into summation of xi into ln of xi, where xi is equal to mole fraction and n equal to number of molecule. Crystal of CO, H2, N2O, D2O, NO, H2O, etc. don't have perfect order even at 0 Kelvin. Their entropy is not equal to 0. Law of mass action and its thermodynamic derivation. Rate is directly proportional to concentration of A raised to the power A, concentration of B raised to the power B. The rate of chemical reaction is directly proportional to the product of active masses of reactant, with each of the active mass term raised to the power equal to its stoichiometric coefficient in the balanced equation. Mathematical expression of law of mass action. Consider a reversible chemical reaction. AA plus PB gives out CC plus GD. Applying law of mass action to forward reaction, AA plus PB gives out CC plus GD. So rate is directly proportional to the concentration of A raised to the power A, concentration of B raised to the power B. RF is equal to KF into concentration of A raised to the power A, concentration of B raised to the power B. RF is equal to rate of forward reaction and KF is equal to rate constant of reactant. Applying law of mass action to reverse reaction, CC plus CD gives out AA plus BB. So RR is directly proportional to the concentration of C raised to the power C, concentration of D raised to the power D. So RR is equal to KR into concentration of C raised to the power C, concentration of D raised to the power D. RR is equal to rate of reverse reaction and KR is equal to rate constant of product. A and B are molar concentration of A and B respectively. So Rf is equal to Kf into concentration of A raised to the power A and concentration of B raised to the power B. And Rr is equal to Kr into concentration of C raised to the power C and concentration of D raised to the power D. At equilibrium, Rf is equal to Rr. So Kf into concentration of A raised to the power A into concentration of B raised to the power B is equal to Kr into concentration of C raised to the power C concentration of D raised to the power D. So K equilibrium is equal to Kf by Kr equal to concentration of C raised to the power C into concentration of D raised to the power D by concentration of A raised to the power A into concentration of B raised to the power B. K equilibrium is equal to equilibrium constant of reaction and equation star represent law of chemical equilibrium. Thermodynamic derivation. Consider a general reversible chemical reaction where the reactant of the product are assumed to be an ideal gas. AA plus BB gives out CC plus GD. We know that chemical potential, that is Gibbs free energy of reactant consisting of A moles of A and B moles of B is given by expression G reactant is equal to A mu A plus B mu B, equation 1, where mu and mu B are chemical potentials of A and B. Similarly, for products we have P product is equal to C mu C plus T mu D, equation 2. In each case, pressure and temperature are constant. The free energy of reaction is equal to difference between free energy of product and that of reactant. That is delta G reaction is equal to G product minus G reactant equal to C mu C plus T mu D minus of A mu A plus B mu B, equation 3. At equilibrium, delta G equal to 0. So equation 3 is equal to 0. Equation 4. The chemical potential of ith species in gaseous state is given by mu I is equal to mu I naught plus RT into ln of Pi, equation 5, where Pi equal to partial pressure of ith component, mu I naught equal to standard chemical potential, that is when partial pressure of the ith component is unity. From equation 4 and 5, bracket start C of mu C naught plus RT into ln of PC plus T of mu D naught plus RT into ln of PD, bracket close, minus bracket start A into of mu A naught plus RT into ln of PA plus B of mu B naught plus RT into ln of PB, bracket close, equal to 0. So bracket start C mu C naught plus C R T into ln of PC plus T mu D naught plus T R T into ln of PD, bracket close, minus bracket start A mu A naught plus A R T into ln of PA plus P mu B naught plus P R T into ln of PB, bracket close, equal to 0. Bracket start C R T into ln of PC plus T R T into ln of PD, bracket close, minus bracket start A R T into ln of PA plus B R T ln of PB, bracket close, equal to minus of bracket start C mu C naught plus T mu D naught minus A mu A naught plus B mu B naught, bracket close. C bracket start RT into ln of P C to the power C plus RT into ln of P D to the power D, bracket close, minus RT into ln of PA to the power A plus RT into ln of PB to the power B, bracket close, equal to minus of bracket start C mu C naught plus T mu D naught minus bracket of A mu A naught plus B mu B naught, bracket close, bracket close. So RT into ln of P C to the power C into P D to the power D minus RT into ln of P A to the power A P B to the PB to the power B, equal to minus bracket start C mu C naught plus T mu D naught minus A mu A naught plus B mu B naught. RT into ln of P C to the power C P D to the power D by P A to the power A P B to the power B, equal to minus G naught product plus G naught reaction. Reactant RT into ln of P C to the power C P D to the power D by P A to the power A P B to the power B equal to minus delta G naught reaction equation 6. So P C to the power C P D to the power D by P A to the power A P B to the power B equal to E to the power minus delta G naught by RT equation 7. Since delta G naught depends only on temperature and R gas constant, so right hand side of equation 7 is constant at constant temperature. Thus P C to the power C P D to the power D by P A to the power A P B to the power B equal to constant equal to Kp, equation 8. Equation 8 is called the law of chemical equilibrium. From equation 6 and 8, RT into ln of Kp equal to minus delta G naught, or delta G naught is equal to minus RT into ln of Kp, equation 9, Van 't Hoff reaction isotherm. This equation shows relation between equilibrium constant and free energy. If the chemical potential are expressed in terms of mole fraction xi, then mu I equal to mu I naught plus RT into ln of xi and delta G naught equal to minus RT into ln of kx. If chemical potential are expressed in terms of molar concentration Ci, then mu I equal to mu I naught plus RT into ln of Ci and delta G naught equal to minus RT into ln of Kc. If the reactant and product are not ideal gas, then thermodynamic equilibrium constant K thermal is defined as equal to A D to the power D, A C to the power C by A B to the power B and A to the power A, where A is the activity. For non-ideal gas, that is real gas, K is equal to Kf equal to Fc to the power C, Fd to the power D by Fa to the power A, Fb to the power B, where F is equal to fugacity. For a mixture of real gases, mu psi I equal to Fi by Pi. So, Van 't Hoff reaction isotherm, it follows Kp is equal to E to the power minus delta G naught by RT, or delta G naught equal to minus RT into ln of Kp. This equation is known as Van 't Hoff reaction isotherm. Clapeyron equation and its application. When the system is in equilibrium, then free energy delta G equal to 0. In phase 1, it is dg1, phase 2, dg2. When phase 1 is in equilibrium with phase 2, delta G equal to 0, g2 minus g1 equal to 0, equation 1. For equilibrium at temperature T plus Tt and pressure P plus Cp, so G2 plus Tg2 minus of G1 plus Tg1 equal to 0. From equation 1, dg2 minus dg1 equal to 0, dg2 equal to dg1, equation 2. According to thermodynamic, dg is equal to vdp minus sgt. For phase 1, dg1 equal to v1 dp minus s1 dt, equation 3. For phase 2, dg2 equal to v2 dp minus s2 dt, equation 4. Putting values of equation 3 and 4 in equation 2, v2 dp minus s2 dt equal to v1 dp minus s1 dt. v2 minus v1 of dp equal to s2 minus s1 of dt. So delta v dp equal to delta s dt. dp by dt equal to delta s by delta v, equation 5. Where delta v equal to molar volume change and delta s equal to molar entropy change. When phase 1 changes into phase 2, if this change occurs at temperature T and delta H is latent heat of transformation. During change in phase, no change in chemical substance take place, only phase changes. So delta S is equal to delta H by delta T. Putting this value in equation 5, dP by dt equal to delta H by T delta V. Equation star. This equation was first derived by Clapeyron and it is called Clapeyron equation. For melting equilibria, solid to liquid, delta H fusion is equal to latent heat of melting and T is equal to Tf, that is melting temperature. So equation star can be written as dP by dt is equal to delta H fusion by Tf into delta V, equation 6. Delta V is equal to V liquid minus V solid, where V solid is molar volume of solid and V liquid is molar volume of liquid. So equation 6 can be written as dP by dt is equal to delta H fusion by TF into V liquid minus V solid. Yeah, dt by dP equal to TF into V liquid minus V solid by delta H vaporization, equation 7. This equation gives the variation of melting point with pressure. For vaporization equilibrium, that is liquid to vapor, dP by dt is equal to delta H vaporization by Tb into Vv minus Vl, equation 8, where Vv is molar volume of vapor and V liquid is molar volume of liquid. Here Vv is so greater than V liquid, so dP by dt is equal to delta H vaporization by Tb into Vv, equation 9. Vapor behaves like an ideal gas, so P into Vv equal to RT or Vv equal to RT by P. Substituting this value in equation 9, dP by dt is equal to delta H vaporization by RT square into P. 1 by P into dP by dt is equal to delta H vaporization by RT square. D into ln of P by dt is equal to delta H vaporization by RT square, equation 10, that is Clapeyron equation. So equation 10 may be written as D into ln of P is equal to delta H vaporization by RT square into dt. In integrated form, if temperature changes from T1 to Tt and pressure changes from P1 to P2, so integration from P1 to P2 of d ln P equal to integration from limits T1 to T2 delta H vaporization by RT square into dt. So ln of P2 by P1 is equal to delta H vaporization by R into 1 by T1 minus 1 by T2. 2.303 log of P2 by P1 equal to delta H vaporization by R into T2 minus T1 by T1 into T2. Log of P2 by P1 equal to delta H vaporization by 2.303 R bracket start T2 minus T1 by T1 into T2 bracket close, integrated form. Applications of Clapeyron equation. The Clapeyron equation is used to calculate the vapor pressure of a substance at a given temperature or to determine the latent heat of vaporization. First, calculation of molar heat of vaporization. Vapor pressure of water at 95 degrees Celsius and 100 degrees Celsius are 634 and 760 mm respectively. Calculate molar heat of vaporization if delta H vaporization of water between 95 degrees Celsius and 100 degrees Celsius. So delta H vaporization is equal to 41.363 kilojoule per mole. Second, effect of temperature on vapor pressure of a liquid can be calculated. Third, effect of pressure on boiling point can be calculated. Fourth, for solid vapor equilibrium, the Clapeyron equation for solid vapor equilibrium may be written as dP by dt equal to delta H sublimation by T into of Vg minus Vs, where delta H sublimation is molar heat of sublimation. Partial molar properties. It was introduced by Jean Lewis when extensive property like vapor, pressure, internal energy, enthalpy, entropy, free energy are calculated in closed system that does not change in experimental value. In open system, acts as a function of temperature, pressure, n1, n2 up to n. So dx is equal to curly x by curly t at constant pressure n1 n2 into dt plus curly x by curly p at constant temperature n1 n2 and so on into dp plus curly x by curly ni at constant temperature pressure n2 and so on into dn1 plus curly x by curly n2 at constant temperature pressure n1 and so on into dn2. For two component system, dx is equal to curly x by curly t at constant pressure n1 n2 into dt plus curly x by curly p at constant temperature n1 n2 into dp plus curly x by curly n1 at constant temperature pressure n2 into dn1 plus curly x by curly n2 at constant temperature pressure and n1 into dn2. Partial molar property denoted by capital letter and bar. So dx equal to curly x by curly t at constant pressure n1 n2 into dt plus curly x by curly p at constant temperature n1 n2 into dp plus x1 bar into dn1 plus x2 bar into dn2. Here x1 bar and x2 bar are partial molar properties. The change in extensive property with respect to the number of moles of one component at constant temperature and pressure and number of moles of other component is called partial molar property. Partial molar internal energy or entropy. U is a function of temperature and pressure in closed system, and U is a function of temperature, pressure N1 and 2 in open system. So du is equal to curly u by curly t at constant pressure N1 N2 into dt plus curly u by curly p at constant temperature N1 N2 into dp plus curly u by curly N1 at constant temperature pressure N2 into dN1 plus curly u by curly N2 at constant temperature pressure N1 into dN2. Here curly u by curly n1 at constant temperature pressure n2 equal to u1 bar and curly u by curly n2 at constant temperature pressure n1 equal to u2 bar. Du is equal to curly u by curly t at constant pressure n1 n2 into dt plus curly u by curly p at constant temperature n1 n2 into dp plus u1 bar dn1 plus u2 bar dn2. Chemical potential. The partial molar Gibbs free energy is called chemical potential and it is denoted by mu I, where mu I is equal to curly G by curly Ni at constant temperature, pressure N1, N2 and so on. Change in Gibbs free energy with respect to the number of moles of component at constant temperature, pressure and number of moles of other component in a system called mu I. Suppose number of component equal to n. Moles of different component is equal to n1, n2 and so on. In open system we know G is a function of temperature, pressure n1, n2 and so on equation 1. G delta G is equal dg is equal to curly G by curly T at constant pressure n1 n2 into dt plus curly G by curly P at constant temperature n1 n2 into dp plus curly G by curly n1 at constant temperature pressure n2 into dn1 plus curly G by curly n2 at constant temperature pressure and n1 into dn2 equation 2. So dg is equal to curly G by curly T at constant pressure n1 n2 into dt plus curly G by curly P at constant temperature n1 n2 into dp plus mu1 dn1 plus mu2 dn2 equation 3. At constant temperature and pressure, integration of dg is equal to mu1 into integration of dn1 plus mu2 into integration of dn2 equation 4. On integrating, g is equal to mu1 n1 plus mu2 n2 equation 5. On differentiating equation 5, dg is equal to mu1 dn1 plus n1 into d mu1 plus mu2 dn2 plus n2 into d mu2 equation 6. On rearranging this equation, dg is equal to mu1 dn1 plus mu2 dn2 plus n1 dn1 mu1 plus n2 into d mu2 equation 7. Putting values of equation 4 in equation 7, dg is equal to dg plus n1 d mu1 plus n2 d mu2. So 0 is equal to n1 d mu1 plus n2 into d mu2. So n1 d mu1 plus n2 d mu2 equal to 0, which is Gibbs-Duhem equation. Phase diagram. First, water system. System consists of three phases: ice, solid to water, liquid to vapor, gas. The phase diagram consists of first three stable curve OA, OB, OC and one metastable curve OA dash. Second, three areas. Third, definite point O. Curves OA. Vapor pressure curve of water representing equilibrium between liquid water and vapor at different temperature. The curve starts from point O, the freezing point of water, and ends at A, the critical temperature beyond which two phases merge into each other. The water vapor system is univariant and it also follows phase rule equation. F is equal to C minus P plus 2. F is equal to 1 minus 2 plus 2 equal to 1. Second, OA dash. The dotted curve OA dash, a continuation of curve OA, represent vapor pressure curve of supercooled water. It is a metastable curve on slight disturbance. Supercooled phase at one changes to solid ice and curve merges into OB. Third, OB. It is sublimation curve or vapor pressure curve of ice. It gives various values of temperature and pressure at which ice and vapor can exist together. It is obtained by studying the effect of pressure on freezing point of water. The curve starts from point O and ends at point B. Ice vapor system is univariant. Fourth, OC. It is melting point curve of ice. It shows the effect of pressure on the melting point of ice. The slope of curve OC clearly indicates melting point of ice is lowered by increase of pressure. This fact is in agreement with Clapeyron equation. However, there is no limit for curve OC and the system is univariate. Second, areas. The areas, that is region beyond the two lines, gives the condition of temperature and pressure under which the single phase, that is ice, liquid, water or vapor, is capable of stable existence. In area below AOB, water vapor, area BOC, ice, area COA, liquid water. These areas are bivariant as to locate any point in areas, temperature as well as pressure must be fixed, indicating 2 degrees of freedom. Also follows phase rule equation F is equal to C minus P plus 2, that is 2. Third, triple point. It is the point where OA, OB, OC meet. At this point, the three phase ice, water, and vapor are in equilibrium. It is only point indicating that there is only one set of condition under which it is possible for the three phases to exist together. The point O is well defined, corresponding to definite temperature of 0.0075 degrees Celsius and definite pressure of 4.58 mm. If either pressure or temperature is changed, then one of the three phases will disappear. It is invariant, also follows phase rule equation F is equal to 1 minus 3 plus 2 equal to 0. Second, sulfur system. One component system comprising more than one solid phase. It consists of four phases: rhombic sulfur, monoclinic sulfur, sulfur vapor, sulfur liquid. According to phase rule equation, all the four phases cannot coexist in equilibrium. This is because F is equal to 1 minus 4 plus 2 equal to minus 1. Meaningless. For a system consisting of a single component, it is not possible to have four phases together in equilibrium. The diagram consists of six stable curves BO, OA, AE, OC, AC, and CF. Four metastable curves OD, OG, AD, CO. First, areas. The areas are bivariant because to locate any point in areas, both temperature and pressure are to be fixed. In area, there are 2 degrees of freedom. Also follows from phase rule equation F is equal to 1 minus 1 plus 2 equal to 2. Area to left of BOCF only SR. Area below BOAE only SV. Right to FCAE only SL. And closed by OCA only SM. Second, curves. First, OB. Sublimation curve of rhombic sulfur. Two phases present in equilibrium along this curve are SR and SV. Curve starts from point O, the transition temperature of SR and SM, and ends at B. If heating is done rapidly, then it is possible to heat SR above transition point along OD. OD is metastable curve and on slight disturbance it merges into curve OA, the vapor pressure curve of monoclinic sulfur. Second, OA. Sublimation curve of monoclinic sulfur. The two phases present in equilibrium along this curve are SM and SV. The curve starts from point A and ends at O. Except at point O, where three phases SR, SM, and SV are in equilibrium, at any other point all along curve, only two phases SV and SM are in equilibrium. Here, degree of freedom is 1. If temperature is lowered, SM, it generally would change to SR at 95.5 degrees Celsius. But it is possible to prevent this conversion by carefully coding it. Then we will go along curve OG, which is metastable vapor pressure curve of monoclinic sulfur. Third, AE, vapor pressure curve of solid or liquid sulfur. The two phases present in equilibrium along this curve are SL and SV. Curve starts at A and ends at E. System has only 1 degree of freedom. The dotted curve AD is continuation curve of AE and represent metastable vaporization curve of liquid sulfur. Fourth AC. Melting point curve of monoclinic sulfur represent equilibrium between SM and SL obtained from effect of pressure on melting point of SM. The curve is inclined away from pressure axis showing that melting point is raised by rise of pressure. Curve is univariant. Fifth OC. It is transition curve. It represents equilibrium between SR and SM and is obtained from effect of pressure on transition temperature of SR. Slope OC is away from vertical pressure axis indicating transition temperature is raised by rise of pressure. Sixth CD. Metastable melting point curve of SR. It represents equilibrium between SR and SL. Since OC and AC meet at C, for which the conditions are 155 degrees Celsius and 1290 atmosphere. 3 triple point. There are 3 triple points, that is O, A and C. At point O, 3 phases are in equilibrium, that is SR, SM and SV. If one of variable is changed, one of phases disappear. Similarly, A is the triple point between SM, SV and SL. Point is invariant. C is the equilibrium between SR, SM and SL. Has no degree of freedom. This also follows phase rule equation. F is equal to 1 minus 3 plus 2 equal to 0 and D is the metastable point. Two component system in which it is possible to express the position of all phases in terms of two substance. F is equal to C minus P plus 2 equal to 2 minus 1 plus 2 equal to 3. In case of system consisting of only solid and liquid phases, small changes of pressure have very little effect on system. Such system are called condensed system. Now, number of degree of freedom in such a case is reduced by 1. Reduce phase rule equation as F dash is equal to C minus P plus 1. Type 1. Those in which two components do not react with each other but simply mix into each other into molten state. Example, BICD system, PBAG system. Type 2. Those in which two components react with each other resulting into formation of a compound. Example, magnesium zinc system, FeCl3 water system, NaCl water. A. Those which result in formation of compound with congruent melting point. Example, FeCl3 water, MgZn. B. Those which result in formation of compound with incongruent melting point. Example, NaCl water. Congruent melting point. The system in which the two pure components react to form a compound which is stable up to its melting point. At this melting point, it melts to give a liquid of same composition. The compound then formed is said to have congruent melting point. Incongruent melting point. Those two component system in which compound form does not remain stable up to melting point. When such a compound is heated, it starts decomposing before melting point to give a new solid phase. When this happens, compound is said to undergo a transition reaction and said to have incongruent melting point. Phase rule. For two component system, F is equal to C minus P plus 2, F is equal to 4 minus P. If F is equal to maximum and P minimum equal to 1, so F is equal to 4 minus P, F is equal to 3, pressure, temperature, concentration. For one component system, F is equal to C minus P plus 2, which is Gibbs phase rule. So F is equal to 3 minus P. If F minimum, so P maximum equal to 3. If F maximum, P minimum equal to 1. For F minimum, 3 minus 3 equal to 0, invariant triple point. For F maximum, 3 minus 1 equal to 2. F maximum equal to 2, that is pressure and temperature. 3D graph is difficult to make, so we will keep pressure equal to constant and we will modify F is equal to 4 minus P. So that f dash is equal to 4 minus p minus 1, that is f dash is equal to 3 minus p, which is reduced Gibbs equation. If system A is miscible and system B is non-miscible, for miscible we get eutectic mixture, mixture with congruent melting point or incongruent melting point. Eutectic system. For two component system A and B in liquid state they are miscible, so F dash is equal to 3 minus P. For F maximum 3 minus 1 equal to 2, that is temperature, pressure constant and concentration. Eutectic point. The eutectic point is the lowest temperature at which the liquid phase is stable at a given pressure. A eutectic system is a homogeneous solid mixture of two or more substances that forms a deep superlattice that solidifies at a temperature lower than any of the individual ingredients' melting point. Third, lead silver system. It is a two component system consisting of two component lead and silver. The various phases possible are A. Solid lead, second solid silver, third solution of lead and silver in molten state, and 4 vapor. Since small effect or changes of pressure have negligible effect on equilibrium existing between Pb and Ag in solid state, so we can use the reduced phase rule equation. F dash is equal to C minus P plus 1. When F dash equal to 0, P is equal to 3. Maximum number of phases that can coexist would be 3. The equilibrium diagram consists of two curves intersecting at point O and eutectic point 0, O. First curve, curve OA. It represents freezing point curve of Ag to which successive small quantities of lead are added. Point A indicates melting point of pure silver. It is observed that melting point of silver is lowered gradually by addition of lead into it. All along this curve, added lead goes into the solution and separation of Ag occurs till point O is reached. At this point, no more Pb goes into solution as solution becomes saturated with respect to lead and hence melting point of Ag does not fall further. Point O represents lowest possible temperature in system that correspond to fixed composition, that is 2.6 percentage of Ag and 97.4 percentage of Pb. Point O is called eutectic point. All along curve OAO, two phases solid Ag and liquid. System is univariant, that is F dash is equal to 1. Second, curve BO. It represents freezing point curve of Pb to which successive amount of Ag are added. Point B represents melting point of pure lead. Addition of silver to lead lowers melting point of lead. All along curve Ag which is added goes into solution while separation of Pb takes place. It continues till point O is reached. At point O, no more Ag goes into the solution and solution is said to become saturated. Hence, melting point of lead does not fall any further. Along curve PO, two phases solid Pb and liquid melt. F dash is equal to 1, system is univariant. Second, eutectic point O. This is point O where AO and BO meet. At this point, solid Pb, solid Ag are in equilibrium with fused mass, that is 3 phases are present. According to reduced phase rule equation, F dash is equal to C minus P plus 1 equal to 0. Point O represents lowest possible temperature below which a liquid phase cannot exist and above which liquid phase cannot be enriched in either component. Such a liquid mixture of two component Ag and Pb which has lowest freezing point compared to all other liquid mixture is called eutectic mixture. Temperature corresponding to eutectic point O is called eutectic temperature. Patterson's process. It is the method of removing silver from lead. The process is based on fact that lead with less Ag solidify first when melted, leaving the remaining liquid richer in Ag. Desilverization of lead. It is the process of extracting silver from a metal such as lead. The argentinoferrous lead containing small percentage of Ag is first heated to a temperature well above its melting point, so system consists only of liquid phase. Then allowed to cool gradually without any change in concentration, then lead starts separating and solution will contain respectively increasing amounts of silver. 4. Bismuthum cadmium system. It is an example of two component system involving solid liquid equilibria forms a simple eutectic. Various possible phases are first solid Bi, second solid Cd, third solution of Pi in Cd or vice versa for vapor. Small changes of pressure have negligible effect on equilibria existing between different phases in solid state. According to phase rule equation, F dash is equal to 0, P equal to 3. Maximum number of phases that can coexist would be 3. First curve. Curve AO. It represents freezing point curve of bismuth to which different amount of cadmium are added. The point A represents melting point or freezing point of pure Bi. It is observed that melting point of Pi is lowered gradually by addition of Cd to it. All along curve, added Cd goes into solution and separation of Pi occurs till point O is reached. At this point, no more Cd goes into solution as solution becomes saturated with respect to cadmium and melting point of Pi does not fall further. So F dash is equal to one system is univariant. Second, curve BO. It represents the freezing point curve of cadmium to which different amounts of Bi are added. The point B represents melting point of pure cadmium. It is observed melting point of cadmium decreases as more and more Bi is added into it. All along this curve, added Bi goes to solution and separation of solid Cd takes place. It continues till point O is reached. Two phases solid Cd and liquid melt are in equilibria, so F dash is equal to one system is univariant and line Cd represent final freezing point. AO is not only freezing point curve of Pi but may also be considered as solubility curve of Pi because the points on this curve represent solubilities of Pi in molten Cd at various temperature. Similarly, curve PO. Second, eutectic point O. This is point where two curve AO and BO meet. At this point, solid Bi and solid Cd are in equilibrium with melt, that is three phases are present. According to reduced phase rule equation, F dash is equal to 0 and point O represent lowest possible temperature below which liquid phase cannot exist and above which liquid phase cannot be enriched in either component by freezing out other component. The temperature corresponding to eutectic point is O is called eutectic temperature. This is always lower than the melting point of component constituting the eutectic mixture. Derivation of Gibbs phase rule. Consider a heterogeneous system consisting of C component distributed among P phases. Number of degree of freedom of system is equal to number of independent variable. Variable temperature and pressure equal to 2. Concentration x1 p1 plus x2 p1 plus x3 p1 and so on. So x and x2 p2, x1 p2, x2 p2, x3 p2 and so on. x1 p3 plus x2 p3 plus x3 p3 and so on. Where cc into component into p. Total variable equal to 2 plus ccp, that is cp plus 2. Restriction, first summation xi into p equal to 1, that is total restriction is equal to p. Second, chemical potential mu. So mu 1 p1 equal to mu 1 p2 equal to mu 1 p3 up to mu 1 p. Similarly, mu 2 p1 equal to mu 2 p2 equal to mu 2 p3 and so on. Total C of p minus 1. Third, chemical affinity AFI equal to 0, that equal to R dash. Total restrictions P plus C of P plus P minus 1 plus R dash. Total variable Cp plus 2 minus bracket start P plus C of P minus 1 plus R dash bracket close. At equilibrium, since no reaction take place, so affinity equation equal to 0. So F is equal to C minus P plus 2. कॉन्ग्रुएंट मेल्टिंग पॉइंट. कॉन्ग्रुएंट मेल्टिंग पॉइंट पर ए और बी को हम सेपरेट नहीं कर सकते एंड कॉन्ग्रुएंट मेल्टिंग पॉइंट से ऊपर ए प्लस बी लिक्विड है और कूल करने पर ए बी सॉलिड मिलता है. फेरिक क्लोराइड वाटर सिस्टम. P is equal to 2, C equal to 2, so F dash is equal to 1. It is example of two component system with congruent melting point. In this system, ferric chloride and water react to form four metastable hydrates, namely Fe2Cl6.12H2O, Fe2Cl6.7H2O, Fe2Cl6.5H2, and Fe2Cl6.4H2O. Double formula of ferric chloride is used to avoid fractional number of water of crystallization. Each of these hydrate possesses a congruent melting point. It also includes two more solid phases, that is anhydrous Fe2Cl6 and ice, one solution phase and one gaseous phase. First, curve AB and point B. Point A represents freezing point of water. Curve AB represents freezing curve of water to which increasing amount of FeCl3 have been added. When point B is reached, solution is saturated with hydrate Fe2Cl6.12H2O, which then starts separating along with ice. So point B is cyrohydric point or quadruple point. F is equal to 0, so system is invariant, and point B is the eutectic point. Second, curve BC and point C. As more FeCl3 is added, ice phase disappears, and now there are three phases in equilibrium. That is solid Fe2Cl6.12H2O, saturated solution, and vapor. Here F is equal to 1, system is univariant, and all along curve BC two phases are in equilibrium. That is solid Fe2Cl6.12H2 and saturated solution. So curve BC represents the solubility curve of Fe2Cl6.12H2O. At point C, saturated solution have same composition as solid Fe2Cl6.12H2O. So point C is the congruent melting point. Third, curve CD and point D. On further adding FeCl3, melting point of Fe2Cl6.12H2O decreases and curve CD is followed. Curve CD represents melting curve of Fe2Cl6.12H2O. At point D, new solid phase, that is Fe2Cl6.7H2, starts separating out. At point D, which is the quadruple point, four phases are in equilibrium. Fe2Cl6.12H2, Fe2Cl6.7H2, saturated solution, and vapor. System is invariant because F equal to 0. Point D is the eutectic point or transition point representing transition. Third, curve DE and point E. Like curve BC, D is the solubility curve of Fe2Cl6.7H2O, and point E is the congruent melting point of Fe2Cl6.7H2O. 5. Curve EF and point E. Like curve CD, EF is the melting curve of Fe2Cl6.7H2O. Point F is the quadruple point, and four phases are in equilibrium. Fe2Cl6.7H2O, Fe2Cl6.5H2O, saturated solution, and vapor. Point F is the transition point which represents transition between Fe2Cl6.7H2 and Fe2Cl6.5H2O. 6. Curve FG and point G. FG is the solubility curve of Fe2Cl6.5H2, and point G is the congruent melting point of Fe2Cl6.5H2. 7. Curve GH and point H. GH curve is the melting curve of Fe2Cl6.5H2O, and H is the transition point where new solid phase is making appearance, that is Fe2Cl6.4H2O. 8. Curve HJ and point J. Curve HJ is the solubility curve of Fe2Cl6.4H2, and point J is the congruent melting point of Fe2Cl6.4H2O. 9. Curve JK and point K. Curve JK is the melting curve of Fe2Cl6.4H2O. Point K is the anhydrous Fe2Cl6 separate out, and quadruple point as well as transition point. Curve KL, which is the solubility curve of anhydrous Fe2Cl6. Copper sulfate water system. Copper sulfate and water combine to form number of hydrates such as CuSO4.5H2O, CuSO4.3H2O, and CuSO4.H2O. Salt starts dissociating to form lower hydrates and anhydrous salt below their melting point at atmospheric temperature. Following equilibria are set up one after another. First, CuSO4.5H2O to CuSO4.3H2O plus 2 water. Second, CuH2O dot 3 water gives out CuSO4 dot water plus 2 water. CuSO4 dot water gives out CuSO4 plus water. Applying law of chemical equilibria to each and putting P solid equal to 1. For equilibria 1, Kp1 equal to P square water and pH2 is equal to under root Kp1 constant. For equilibrium 2, Kp2 is equal to P square water and P water is equal to under root Kp2 which is constant. For equilibria 3, Kp3 is equal to P water and pH2 is equal to Kp3 equal to constant. For each above equilibria, vapor pressure of water vapor become constant at constant temperature. Instead of keeping pressure constant and increasing temperature till dissociation equilibria is reached or attained. In this method, we used to study salt hydrate at constant temperature and pressure continuously decreasing till dehydration of salt start and dissociation equilibria is set up. For equilibria, P water equal to 7.8 mm, for equilibria 2, P water equal to 5.6 mm, and for equilibria 3, P water is equal to 0.8 mm. Each of three equilibria discussed above involves two solid, one gas, so number of phases equal to 3. Applying phase rule equation F is equal to 1. Similar results are obtained if temperature is higher. Higher the temperature, higher the vapor pressure. Above 102 degrees Celsius, pentahydrate not stable. CuSO4.3H2O is the first stable hydrate. For definite vapor pressure to exist, two solid phase must be in equilibrium with water vapor. Hydrated salt has no vapor pressure of its own. Vapor pressure for different equilibria 1 to 3 or in general for any other salt hydrates are independent of amount of the salts present. Thank you.